Hi, everyone. My name is Zanie Blue, and I work on the Astral team, now recently acquired by OpenAI. I'm focused on improving the developer experience in the Python ecosystem, and today I'll be talking about the complex operations that power performant package management. I'm one of the creators of UV, so we'll be using that as our primary lens. We'll start with something nice and simple. You've got a fresh clone of Flask, and you want to run it. So what needs to happen here? UV's responsibility is to ensure that the environment is ready before executing the command. There are three high-level phases to that end: discovery, locking, and syncing. Oh, those are the three. Discovery is when UV collects context on where and how it's being invoked. We answer questions like, what UV settings are being used? What project are we in? Is the project a workspace? And then we need to determine what Python version to use. So we have questions like, what is the Python version request? Is there an existing virtual environment? What Python versions are available? Locking is the process of determining the packages that are needed and recording that information in a lock file for subsequent use. Here we have questions like, is there an existing lock file? What are the dependencies of the project? What are the transitive dependencies of those dependencies? What sources should be used? What versions satisfy the constraints? And are the dependencies conditional on things like Python version or platform? Last but not least is syncing. During syncing, we take the lock file and materialize it into a concrete environment. Here the questions are like, what subset of the lock file is selected? Do you have groups enabled? Are you selecting extras? Do we need to create an environment? What packages are in that environment, if there is one? What packages do we need to download? What packages do we need to build? And what packages need to be installed and uninstalled? Now, I wrote those all out and I thought, that's a lot of questions. How long do you guys think that takes? Assuming we have a machine that's never used UV, these are the rough benchmarks for Flask. Discovery takes about 50 milliseconds, locking takes 750 milliseconds, and syncing takes 3 seconds. That brings us to a total of 4 seconds. That's not so fast. Wasn't the pitch that UV is fast? Isn't it written in Rust? Nobody would use UV run if it added 4 seconds to every command. Instead, they would use older workflows where you activate the environment one time and then manually sync it as needed. I really don't want people to have to do that because then you have to pay a lot of cognitive overhead to know if your environment is in the right state when you're working on your project. And generally, these questions are things where the answer can be determined efficiently by the machine. The nuance here is that those numbers are for what we call a cold operation. The UV cache has not been populated. It doesn't know anything about your system or your project. The lock step needs to fetch metadata for every dependency from the package index. The sync step needs to download all of the packages and build wheels. If this operation were warm, which is where the cache is populated, but there is no lock file or virtual environment, it's much faster. Locking goes down to 15 milliseconds, and syncing goes down to 100 milliseconds. And if the operation were hot, in which case the UV lock exists and an environment already exists in the project, and we just need to audit those, UV is very fast, around 10 milliseconds. To put this in perspective, 10 milliseconds is faster than the Python startup time. So for most Python projects, this is entirely negligible. Next, we're going to talk through each of these operations in depth, what needs to happen to answer all of those questions I posed, and what UV is doing in each of these cases to yield such a dramatic speed up. First, we'll start with discovery. The first thing UV does is determine its own settings. This operation is fairly cheap. We don't need to traverse a big file tree because we don't read configuration files from child directories. Instead, we walk up from the current directory until we get to the root of the machine. And we check for a UV.toml file at every layer. Then we also check for uv.toml at a couple well-known locations for user and system level configuration. Next, we need to discover the project root. Similar to settings discovery, UV traverses upwards to determine which project is being used, except for here we're looking for a pyproject.toml. Even if you've changed into a subdirectory, like the test directory here, UV will still know you're in this project when you're running commands. After finding a pyproject.toml, we need to keep going to see if there's a workspace root above it, since a workspace can define additional settings and metadata for the project. This is an example workspace, as well as the configuration for finding the members. After finding the workspace root, we need to materialize the configuration and metadata of all of the workspace members. This is because UV locks the entire workspace together. And this involves iteratively discovering all the members, like using that glob there, and then reading all their pyproject.tomls. There are some interesting pathological cases here at scale. For example, in Airflow, which has a really large workspace, just reading the toml files can take over 100 milliseconds. And we need to know if the settings have changed, so we actually can't skip this step. There's not really a way to optimize it. We'll pay this cost on every UV operation, even the hot path. We're actively working on some optimizations for this. So for example, in this heat map, we are reading the pyproject.tomls multiple times. And so we're adding in-memory caching to UV, so in a single operation, we don't do that read and parse loop more than once. So that's all the settings discovery. Next, we're gonna figure out what the Python version request is. This can come from multiple sources, and the first thing that we do is determine the requires Python range. If you're just using a single project, this is pulled straight from the pyproject.toml, but if you're using a workspace, we need to take the intersection of all of the requires Python definitions in order to determine the effective range for your project. Then we'll see if there's a request for a specific Python version. This can come from Python version files, which are these .python-version files, which requires yet another parent directory traversal. It can also come from the command line or environment variables. If there's not an explicit request, we'll just use the requires Python range as the effective user request. Once we have the Python request, we can see if there's an environment that matches it. In the hot case where an environment exists and matches the request, UV needs to do very little work. It can skip the entire Python version discovery process. If it doesn't match the request, we'll ignore the environment and remove it later on sync. So if the environment isn't sufficient, we need to find which Python versions are available. We'll start with the managed Python versions. These are Python versions that UV has installed. These are not only the easiest case, but generally UV prefers to use these versions over ones on the system. This case is easy because UV does not need to invoke the Python interpreter in order to determine if it's usable. UV encodes all of the information necessary to know whether or not the interpreter is usable in the directory name. This includes the version, the operating system, the architecture, and the libc. In contrast, discovering Python versions from arbitrary executables on the path is quite a bit more complicated. To determine if an executable is actually usable, UV needs to run it. Unfortunately, running a Python interpreter is quite slow on the timescales that we're talking about. The startup is at least 20 milliseconds, and if we need to query many executables on the system, this cost can really add up. So UV has some heuristics to reduce the number of Python executables that it needs to query. For example, if your Python version request is for 3.13, UV will not bother querying an executable that has the name Python 3.14. It's possible for there to be false positives in this, but in general, it's pretty unlikely. The next way that UV makes this faster is that it caches interpreter metadata. The interpreter metadata that we're retrieving includes things like the Python version, the architecture of the interpreter, whether it's a debug build, etc., everything that we need in order to use that interpreter. This means on a warm discovery, UV will look at the modified time of the executable, and if there is an entry in the cache for that executable, UV can skip querying it again. We store these cache entries using a packed binary format called message pack. This is just faster to serialize and deserialize than JSON, but it's basically a small blob. Another optimization for Python version discovery is that UV uses lazy iterators. So as soon as we find a usable interpreter, it can stop searching, which minimizes the amount of system calls we need to make to list directories, as well as interpreter invocations. This design is not without downsides, though. It means that when you do a command like UV Python list, UV will query each interpreter sequentially, even though it's basically an embarrassingly parallel operation. I've seen this take like over 10 seconds on some Windows machines with a lot of Python interpreters on it, which is always really sad to see. So I have some work in progress that allows us to discover in parallel, which gives us a big speed up in the rare case that we actually want to find every interpreter on the system. All right, we've made it through the first 50 milliseconds or so. Only 4 more seconds left. Next, we're going to talk about locking, in which we determine which versions of packages should be used. First, we check if there's an existing lock file. If so, we need to determine if the lock file is consistent with the input requirements and settings. So if you change something in your pyproject.toml or you change a resolution option, that lock file is not usable. If the lock file is usable, we're done. We move immediately to syncing from the lock file. This is what makes the lock step so fast in the hot case. If there's not a usable lock file, we need to perform a resolution, which is this iterative process of determining compatible package versions. The first step of resolution is to determine the dependencies of the project. We've already loaded all the relevant files during discovery, but we didn't parse the dependencies yet to avoid that upfront work. Not all UV operations that perform discovery need to perform a resolution. Here we parse them from strings into UV's representation of requirements. Then for each dependency, we need to determine their dependencies. And this is where things start to get pretty complicated in resolution, because then we need the dependencies of those dependencies. And the dependencies of a package can vary across the version of a package. So there is a lot of possible metadata for UV to retrieve. The process of retrieving this metadata is by far the slowest part of resolution. So we're going to spend a fair amount of time here. First, we need to fetch all the versions and distributions for the package. We do this by making a request to the simple API, which is the standard interface for a Python package registry. We make this request per package that the project needs. The response includes the versions of the packages that are available and some details about the files associated with each of those versions. We'll use this later to determine the download URLs and things for wheels and source distributions. UV caches this data respecting HTTP cache control headers. For PyPI, this response has a 10-minute time to live. So if a new version of a package comes out, UV might take 10 minutes to refresh its cache entry to recognize that version. We store this data in our cache as an archive entry. Archive is a really cool library. It's a Rust crate that allows us to do zero-copy deserialization. In general, allocations are a slow part of computing, and what archive does is on a warm cache hit, when we already have this response for the simple API, UV will read that entire response into memory, allocating one time, and then does not need to do any allocations to present a structured view of that data. This is in contrast to like reading something like JSON, where you need to do an allocation for every single string that you encounter as you deserialize that file. UV only needs to perform additional transformations and allocations when the resolver actually considers one of the many versions represented in this response. For most resolves, we don't actually need to visit many versions, so this saves a lot of unnecessary work. Next, we need to actually fetch the metadata for each package version that we're considering to understand their dependencies. We'll only do this once we're considering using that version during resolution. On the happy path, we can fetch this metadata directly from the index, which will give us a metadata file in this glorious email header format that we use for wheel metadata. Similar to the simple API, we cache this response. We use message pack here instead of archive because archive imposes strict constraints on our internal data types for safety serialization that zero cost deserialization does come at the cost of some flexibility, and in this case, the performance benefits don't justify that complexity. Another difference from the simple API cache is that there's no expiration time on these entries. Wheel metadata is considered immutable, and so UV can cache this forever or until you clean your cache. Earlier, I said that reading the metadata directly from the index was the happy path, and there are a lot of sad paths. Not all indexes support metadata fetching, and so there is a slower path in which we need to extract the metadata from the wheel itself. If possible, UV uses HTTP range requests to avoid downloading the entire wheel just to determine its dependencies. We can use range requests because wheels are just zip files, and zip files have this central directory at the end enumerating all the files in the archive as well as their offsets. So UV retrieves a chunk of the end of the wheel and then uses that to determine the position of the metadata file and then requests the metadata file. This requires multiple range requests, but is much faster than downloading an entire wheel that we might not even use. Remember, we're just trying to figure out what the wheel's dependencies are, not install this package. We also have to consider the case, skipped one. I guess there's also another case where it doesn't support range requests, and then we just do have to download the entire thing and extract it on disk in order to determine its dependencies. There are some annoying commercial package registries which still do not support range requests, and UV is much slower on those. We also have to consider the case where there are no wheels. We'll download the source distribution instead and try to statically extract the metadata from the pyproject.toml, similar to how we did for our own project. However, if there's dynamic metadata or if they're still using a setup.py for some reason, we will need to construct a build environment with its own build dependencies and then invoke the build backend to get the metadata. This actually is sort of loops back on itself. It's recursive because UV needs to perform a new resolution to determine what versions of those build dependencies to use, and it needs to do sort of a mini lock and sync operation. This is even slower and generally not the desirable path during resolution, so it's great when there is these metadata files. Not all packages come from an index. UV allows you to apply sources to dependencies, saying, I want this package to come from a Git repo or a local path or an arbitrary URL. Right now, UV only allows applying sources to first-party dependencies. So at the start of resolution, we have a clear picture of which packages are special cased. There are people that want us to expand that, and I think it's a reasonable ask, but it will add a lot of complexity to determine the source of a package dynamically while we resolve. The handling for these is pretty similar to the cases that we've already been talking about. UV will fetch them from the requested location and apply caching semantics for the fetch. There's like special casing for Git caching that we won't go into here, but it's the same general idea. We'll either be able to read static metadata from the pyproject.toml, or we'll invoke the build backend to get the dependencies for the package. Not all packages come from a single package index either. By default, of course, everything comes from PyPI. However, users can define multiple indexes with a priority order, and UV then, during resolution, needs to determine the proper index to fetch the package from. So as we mentioned earlier, we need to actually solve for compatible versions across all of your dependencies with constraints applied. For example, Flask applies a constraint on each of its dependencies, and those dependencies might apply constraints too. So here we can see both Worksug and Jinja2 apply a constraint on markup safe. So we need to pick a version of markup safe that is compatible with both of those constraints. And once you have a big dependency graph, there can be a lot of different constraints on package versions. This process is actually not that slow. The goal here is mostly to minimize doing the expensive work that we just discussed of network I/O. Part of the way that we do this is with heuristics to avoid iterating through many versions of a single package, reducing the number of metadata fetches that we perform for unusable parts of the package graph. Heuristics are also used to improve the resolution. For example, there are many valid solutions to a dependency graph, but some are more desirable than others. For example, you would usually like the newest versions of packages that satisfy the graph. The actual heuristics that we're using here are out of scope for the talk, but the general idea is that we assign a priority to each package, and then as the resolver iterates, it uses a priority queue to pick the highest priority package. Fetching the metadata is really expensive. I'll keep saying that. So we don't want to be blocked on it. UV uses 2 threads for this, one running the solver and one running metadata fetches. The metadata thread will perform prefetching, in which we actually fetch metadata for packages that we don't know we need yet. We'll basically pick promising candidate versions and fetch that metadata eagerly in the background. This way, the CPU-bound resolution process is never blocked waiting for I/O. Another optimization during resolution is that we need to parse a lot of versions and requirements. So for Flask, which is a pretty small package, it has a small dependency tree, we'll perform about 200,000 version parsing operations and 600,000 version comparisons. For a bigger project like Airflow, we'll perform over 1 million version parsing operation and 12 million version comparisons in a single resolution. Improvements to these hot operations can make a big difference in performance. For example, Andrew, who's sort of an internet legend, implemented this incredible change, making version comparisons way cheaper. The key insight here is that we take the most common type of version, think 1.2.3, and we make that case highly optimized. There are a lot of weird and bespoke version types of versions that exist in the version spec. I do wish it was a little more strict, and UV can still handle those, but by optimizing for the most common versions that we'll encounter in the real world and just taking a slow path on the bespoke things, we can dramatically improve those version parse and comparison operations. One problem with solving version constraints is that dependencies can be conditional on markers. And so markers are like descriptions of the environment, for example, the Python version or the platform. The reason that this is important is because when we are locking, we want to solve for all possible platforms and Python versions in your requires Python range. Otherwise, when you use, have a lock file and you're using UV on another machine, that lock file might not be usable. So by solving for all possible types of platforms, the lock file is always correct for a user. This means that we actually need to split our resolution into multiple child resolutions. So here's a little excerpt from the UV lock file. We call this general process universal resolution, and we implement a forking resolver to do this efficiently. Basically, the resolver can fork many, many times into different sets of markers and resolve different versions for packages during that operation. There could be a whole talk about universal resolution. It's super complicated, so if you're interested, talk to me about that afterwards. Okay, we're done locking, so I'm going to take a sip of water. After we have the lock file, we need to construct an environment for execution. So the first step here is to select a needed subset of the lock file. To do this, we need to determine the root requirements by applying selected groups and extras. These can be toggled via the command line. From there, we'll traverse the graph representation in the lock file to include all the reachable dependencies. At the same time, we'll transform the universal resolution to a platform-specific subset. So we take the markers for the current platform and filter out dependencies that do not match during that graph traversal. Next, we may need to create a virtual environment. we already determined if the current environment was usable during discovery by checking if it had the right Python version. If it's not, we'll delete it now and create a new one. This is generally quite fast, around 20 milliseconds. However, if there was a usable environment, we need to determine which packages are present in it. If there are packages that fulfill some of our requirements, we can skip preparing and installing them. And if there are packages that aren't in our requirements, we may want to uninstall them. To discover which packages are present, we search for distinfo directories. These are standardized directories that contain metadata about the installed packages in the environment, and this allows us to quickly determine which package versions are present in the environment. We compare these to the packages in the resolution to create a set of packages to prepare for installation. The first step in preparing packages for installation is downloading them. In a typical sync operation, UV spends the vast majority of time downloading wheels. That's what takes almost all 3 of those seconds during the cold sync. UV fetches multiple wheels concurrently, starting with the largest files, such that we don't end up waiting for them at the end. And then there's a streaming pipeline where UV downloads, hashes, and extracts the wheel simultaneously. This allows us to mix CPU-heavy work, like hashing and decompression, at the same time as we perform the network I/O. Before a wheel is persisted to the cache, it is validated, for example, by ensuring the record file matches what is present in the wheel. The record file is one of these files in the distinfo for wheels. Here's an example cache layout for the file lock package. I just picked an arbitrary package that would fit on a slide after we've downloaded the wheel. The wheels bucket in our cache, you'll see our cache has different directories. These are buckets, and it has this HTTP file representing UV's cache policy for the artifact. And then alongside that, there is a pointer to the archive bucket. This is where we store the unpacked wheel. We store these unpacked wheels so that we can install them later directly from the cache, and notice we don't store the compressed wheel at all. For packages that don't have a wheel matching the current environment, we'll need to download a source distribution and build it into a wheel locally. We've talked a bit about building source distributions before, but here I'll cover it at sort of a different angle. This is the cache layout for building file lock from a source distribution. We download the source distribution into that sdist bucket, and then we cache it into a directory keyed by the index, the package name, and the version. Source distributions aren't always immutable, so we create another randomized directory name to actually represent this particular revision of the source distribution. And here you can see we sort of like have this source directory that has a little ellipse after it. That is the unpacked source distribution. We also don't store that in a compressed form. We then construct a temporary build environment and invoke the build backend to get a wheel. And the wheel is atomically moved into the cache alongside the source distribution. We then unpack the wheel into the archive bucket to prepare for installation. There's kind of a lot to process here. We do the same thing for arbitrary URL dependencies and Git dependencies with a slightly different layout. The key thing is that they all end up in the archive bucket in the same unpacked format. After all the wheels are prepared in the cache, we can finally sync them into the environment. At this point, UV's unpacked cache entries make a big difference. On macOS, we can reflink an entire directory at once from the cache into the virtual environment. This is just a macOS specific syscall. Reflinks provide copy on write semantics. So when a file is present on both locations, it's not using more disk until one of the locations is modified. Since you're generally not modifying files in your virtual environments, this means that UV can be UV can reduce disk usage by deduplicating installs of packages across many environments, and reflinking is much faster than copying the files. On Linux, we do this file by file. They don't provide a reflink method for entire directories. Most Linux file systems, unfortunately, still don't support copy on write semantics, and so our fallback from that is hard links. Hard links offer the same deduplication benefits. However, if you modify a file in your virtual environment, then you will have modified it in your cache, and you will have modified it in all of your environments, which is sort of an open problem. Hard links, though, are generally worth the performance benefit, and if they cannot be used, for example, if the cache is on a different drive than the environment, UV will just transparently fall back to copying. At this point, we can also uninstall extraneous packages. A Python package can install files into arbitrary locations in the environment, so we can't just delete a directory to remove a package. Instead, we need to read that record file that I referenced earlier, and we'll use that to determine which files belong to a package and then remove all of those. This was actually the cause of a recent low-severity security issue in UV and pip. It's just a kind of a fun fact. The record could list an arbitrary file on the system, and neither of our tools validated that that was, in fact, a location in the environment. And so UV would just happily delete it when you uninstalled the wheel. This generally isn't a big deal because if you're installing malicious packages, you're in trouble anyway, and uninstalling them is like sort of the least of your problems. But now UV will refuse to delete a file if it's outside the environment. And if you recall earlier during installation, I mentioned that we validate that the record actually refers to files in the wheel. That also was added during this change. And basically, if there are invalid entries in the record, UV will just remove them so that this problem can't happen in the first place. Okay, now we have an environment and we can finally run Flask. Now you clap. No, I'm kidding. Thank you for that. So in summary, package managers hide a lot of complexity, and that's complexity that I really don't want you to have to manage when you're working on your projects. And next, I'm going to talk about some high-level strategies that we talked about for managing all this complexity efficiently. So first, we should avoid doing work we won't need. A lot of UV's optimizations are about lazily iterating or only materializing data when needed. However, we should choose to do some work that may be unnecessary when it can speed up the critical path. Think back to the prefetching of metadata. This is often background work that ensures the critical path is not blocked, and if the critical path finishes while we're doing this work, we can just cancel it. Next, we should optimize for the most common cases. Think back to the version parsing. This is not to say you should not support edge cases. UV has invested a lot into correctness on edge cases, but often the common cases are simpler than edge cases and can be special cased to be faster. In hot code paths, this can make a huge difference. And last but not least, avoid redoing work. UV's cache is always on. Even if you use the -- no cache flag, UV will construct a temporary cache because it is such a core part of its data model. The first step in every UV operation is to see if we can avoid doing work at all by reusing a previous result. And we store results in a processed format so that we don't need to do parsing when we load them. Once we don't have to redo these expensive steps, the warm path gets really fast. And once we can optimize cases like auditing the lock file and the environment, we can make the hot path feel instant. I want to note that a lot of these strategies were not viable 10 years ago. Before 2013, there weren't wheels or a standard way to define versions. I know it's a little longer than 10 years ago, but cut me some slack. Before 2015, there wasn't a standard way to define a build backend or dependency markers. Before 2020, there wasn't a pyproject.toml with static dependency metadata. And before 2021, there wasn't wheel metadata serving on indexes, so we always had to take that slow path. It takes years after standardization for adoption to be widespread in the ecosystem. And I think this is a big part of why UV has been so successful. We've capitalized on a point in time where the packaging standards have finally made it possible to build performant workflows and be able to reuse all of that work on each stage of its operations. Here I have a slide that says I don't have time to talk about future work, but I guess I talked faster than normal. So I actually do have a little bit more time, and so I just want to plant some seeds on things that we're thinking about. One thing that we're thinking a lot about is locking of build dependencies. Right now, I said that when we are performing a resolution, we could encounter a package that needs to be built in order to determine that metadata, and also as we're installing wheels, we need to create build environments, if we're installing source distributions, we need to create build environments. Right now, there is not a package manager in the Python ecosystem that locks those build dependencies. This means that when setup tools releases a breaking change, everyone's builds break. And not really to pick on setup tools, but like any build backend is basically locked into not making breaking changes without causing massive disruption in the ecosystem. The problem with locking build dependencies is that it adds a lot of work. Basically, any time that there's a source distribution available for a package, we then need to perform an additional resolution to lock its build dependencies. Even if it has 40 wheels, I think NumPy has 43 wheels for the different platforms they support, we could, in theory, encounter a platform that is not covered by those wheels, at which point we would need to build NumPy. And so this means that UV has to do a lot more child resolutions during that resolution path. I have a draft pull request that I vibe coded that implements this feature. I'm pretty sure it's wrong, but if you want to try it, let me know. I'll hook you up. I'm looking for beta testers. There's some additional things that we can do in the future. So for example, the index could serve responses in message pack instead of JSON. This is actually something that we've done with the package index that Astral's working on, and that allows us to download that directly, and it improves our deserialization times pretty significantly, as well as it's a smaller payload going over the network. We can also make improvements to the serving of metadata in bulk. So often UV needs to retrieve the metadata for many package versions, and right now we have to do a separate network request for all of those. But if we could standardize ways for package indexes to serve that metadata in mass, UV could make a lot less network requests. And finally, there are some open questions around ongoing standardization work. So for example, if you're following wheel variants are going to add a lot of complexity to resolution. And we've actually built out some prototypes in UV, but there is some concern that explosion in the possible types of wheels could dramatically increase the cost of that resolution step. And with that, thank you.